Hello guys, good morning. My name is Savant. I'm a third electrical undergraduate. Today we are looking at some problems where we have to deal with the discrete Fourier transform. Like we already know about the DTFT, discrete time Fourier transform, but this is discrete Fourier transform. So discrete Fourier transform is calculated because to, like, let's say the output of DTFT is continuous, whereas the output of DFT will be discrete, because in all the computers and all the systems worldwide we will be using the discrete values to operate on all such things. So here we are using the DFT. Now, like we all know, the DFT formula is x of k, capital X of k equal to sigma n equal to 0 to n minus m minus 1 x of n into e power minus j 2 pi by n k capital K into small n. So like here we form the matrix of the coefficients using these values, and then taking the input from the sample of 75 samples, we'll be calculating the DFT. So now we'll look at the code. First we take the input of 75 samples, that is 25 hertz and 3 seconds. So it will give us 75 samples. Then I have taken these matrices. Like I'll explain you each and individual matrix. This first XR is the real part of the output. It is a, and XI is the real imaginary part of the output. These both are column matrices. Now WR WI, these are the coefficient matrices. Real coefficient, imaginary coefficients. And this is the sample input. X of 75, these are the column matrix. So let us say to begin, serial dot begin of 9600, like we already know about this, the transfer rate for int I equal to 0. First I calculate this is the moving average filter. We only know about this code for int I equal to 0 less than 75. I have taken the length is equal to 8. So running the code from j equal to 0 to j less than 7, adding all those values, dividing with 7. So in the fill we'll getting the output of moving average filter. Now I taken this moving average filter into this x of I. So I'm taking this as input. I'm taking this as an input. Now for that input I'm taking the like not for that input, from I equal to 0 to I less than 75, I'm calculating the coefficients. This coefficient matrices WR WI, real coefficients, imaginary coefficients. Now I'm calculating the output with the help of this. See, we already know about the formula e power minus j 2 pi by k, 2 pi by n into k into n. So using that we'll be calculating this code. Like in this code we'll be calculating the output, real matrix output, imaginary matrix output. So now we'll be getting the output values xri, xi. That means xr plus j into xi. So with the help of this, I'm calculating I'm taking the another matrix, column matrix, and storing the magnitude of this square root of xr star xr plus x star xi star xi. This gives us the magnitude of the output, magnitude of the Fourier transform, and I'm storing that in the answer value, answer matrix, answer of I of m. This is also column matrix. For this matrix, like for if we plot this value, this output answer I will be getting a curve. I'll show that curve to you. Take 2 minutes. Just wait. Just a few more seconds. Please wait. Yeah. See, this will be the curve. Like if you look at it, the first half is a peak, and the second half is like it is the mirror image of it. Like the second half is the mirror image of the first half. You can see from this. So now what we'll be doing is we'll be calculating the peak value, this value, that index. Okay. So we'll be dividing it into half, and we'll be calculating the maximum value in the first half, and then calculating that index. So looking at that, see here. For int equal to 0, less than 37, because we are taking 75 samples, I'm taking the first half 37. So I'm taking the max value, and I'm not finding that index. So calculating this will gives us the k into fs into 60 by n. My frequency is 25. My number of samples are 75, and I'm calculating the pulse rate for minute, right? So I multiply it into 60. This gives us the pulse rate. We'll be getting around 80. 1 minute. See, we got that. This is the pulse rate for taken sample. Thank you.